Alright everybody, welcome back. In this video we're going to finish up with section 8.3 of AP Calculus using accumulation functions and definite integrals in applied contexts. We're going to pick up where we left off at the end of the last video and look at example 3. Example 3 was from the 2011 AP Calculus AB exam. I should say FR, not RE. I don't know what that's all about. Free response question number 2, calculator section. As a pot of tea cools, the temperature of the tea is modeled by a differentiable function h for 0 is less than or equal to t is less than or equal to 10, where time t is measured in minutes and temperature h of t is measured in degrees Celsius. Values of h of t at selected values of time t are shown in the table below, and you can see the table there. Alright, part B of this question. Using correct units, explain the meaning of 1 over 10 times the integral from 0 to 10 of h of t dt in the context of this problem. Use a trapezoidal sum with the 4 subintervals indicated by the table to estimate this value. Alright, this is a good review of something we talked about a few sections ago. When you see this form 1 over fraction, or 1 over number, and that number just so happens to be the difference between the limits of integration, this is telling you that we're calculating an average value. And so 1 over 10 integral from 0 to 10 of h of t dt is the average value of h of t. Is the average value. Now what does h of t represent? Is the average value for h of t, which is the temperature of the tea. So I'm going to erase this word value here and say this is the average temperature of the tea units for temperature in degrees Celsius over the time interval t equals 0 to t equals 10 minutes. And now I'm supposed to use a trapezoidal sum to calculate this. Notice that we've got non-uniform widths for our trapezoids up here. So we're going to have to calculate each trapezoid individually. So the first trapezoid is 1/2 times 2 times the sum of the bases, 66 plus 60, and 1/2 times 3 times the sum of the bases. And then 1/2 times 4 is my width, times the sum of the bases. And then 1/2 times 1 is my width, times the sum of the bases. And that's my trapezoidal sum that represents the integral from 0 to 10 of h of t dt. Don't forget to multiply that value by 1 over 10 in order to get the average temperature. And now this is a calculator section, so I'm going to go ahead and turn to my calculator. Scroll up a little bit so I've got some room for my calculator, and I'm going to go ahead and use that 1/10 times. I can pull the 1/2 out in front. And then we've got 2 times 66 plus 60 is 126, plus 3 times 112, plus 4 times 96, plus 1 times 87. I think that's enough parentheses. There we go. And we get 52.95 as our average temperature of the tea over that interval. Part C, evaluate the integral from 0 to 10 of h prime of t dt. Using correct units, explain the meaning of the expression in the context of this problem. Okay, so to find this integral, I'm taking the integral from 0 to 10 of h prime of t. So I just find the antiderivative of h prime of t, which is h of t. And you evaluate that from 0 to 10. This is going to be h of 10 minus h of 0. I go to my table up here. H of 10 is 43, and h of 0 is 66. That's negative 23. Is that degrees Fahrenheit? Oh, it's degrees Celsius. Oops. Okay. Using correct units, explain the meaning of the expression in the context of this problem. This is the integral of the change in temperature. So when we integrate change, we get total, and so this represents the total change in temperature. Is the total change in temperature of the T in degrees Celsius. Well, degrees. Notice I said degrees and started writing decrease. In degrees Celsius, total change in the temperature of the T in degrees Celsius over the time interval T equals 0 to T equals 10 minutes. And then the last part here, which is why this problem shows up in this lesson. At time t equals 0, biscuits with temperature 100 degrees Celsius are removed from an oven. The temperature of the biscuits at time t is modeled by a differentiable function b, for which it is known that b prime of t equals negative 13.84 e to the negative 0.173 t. Using the given models, at time t equals 10, how much cooler are the biscuits than the t? So we're trying to figure out how the temperature of the biscuits at time 10. We know the temperature of the biscuits at time 0, and we know that this is the rate of change of the biscuits. So if we integrate that from time 0 to time 10, it's going to give us what we're looking for. Okay, and b of 0 is 100, so I'm going to type this up. I've got 100 plus the integral of negative 13.84 e to the negative 0.173 t with respect to t from 0 to 10. That's 34.183 degrees Celsius. That's the temperature of the biscuits. And the T from our calculations, the T at time 10, we can get that from the table, is 43 degrees Celsius. So 43 minus 34.183 gives me 8.817. As how much cooler the biscuits are than the tea. All right, that brings us to the end of this lesson. Go ahead and do some practice with these problems, and we'll see you next time for section 8.4, finding the area between curves expressed as functions of x. All right, see you then. Have a great rest of your day, everybody. Bye-bye.